Hello and welcome to homework 4 part 1. In this part of the homework we're taking a look at a problem, a similar problem that we've actually taken a look at before in this course, where we have two tanks in series. And what we have here is we have two flow rates going in initially to this first tank here. We'll call it tank 1. And then we have a hole at the bottom of the tank which then drains into the second tank. And the second tank also has another flow rate, we'll call that U3, going into the tank. And then this tank also has a hole in it with fluid going out. So what we are asked to do here is to solve for H1 and H2, and we need to be able to know what H1 and H2 are both initially if we have steady state flow going into the first tank U1 and U2 and then U3. And then we also need to know how this system changes if we were to manipulate either U1, U2, or U3 to see how H1 and H2 would change over time to make sure we're not overflowing our tanks or causing a disruption in our process. So we've done this before, calculating the heights in these tanks by using solve-IDP. However, this time what we're asked to do is to solve it by using transfer functions. And we will do this first by solving for the initial steady state values, H1 and H2. Then we're going to use JAX and Python to basically linearize the dynamic equations. And then from there we'll get our state space model, which we'll go through. And then lastly, we'll go ahead and we'll be able to then solve for H1 and H2, and then actually compare that to the method that we have used before, solve-IDP. So what we have here is we know, I'll go into Python in a minute, and what we're going to start off doing is just solving for our initial steady state values, H1 and H2. But what we know here is we know U1, we know U2, we know U3, we know AH here, so the flow rate leaving the tank. So we have basically all the values that we need, and I'll go ahead and plug those in when we get into Python. But what we can do here is we can take a look at our initial steady state differential equations. So we'll have, to solve for the change in the height of the first tank with respect to time, we'll have the cross-sectional area times dH1 dt. And this will be equal to basically do an in versus out. So going in, we'll have U1 plus U2, and then we will subtract Q1, the flow rate leaving this first tank, Q1. So from here, we can go ahead and just divide over by AC, cross-sectional area tank, which we also know. I'll go ahead and import that in Python when we get there. But this can get us our initial steady state for the height the height in the first tank. And similarly, we can take a similar approach to the second tank, so dH2 dt, and same idea, in versus out. So we have Q1 going in and U3 going in, so we'll have Q1 plus U3, and then we'll subtract out Q2. And we can solve for Q1 and Q2, right, because we have, we'll know the cross-sectional area of the hole. And actually, I believe we're given an alpha value here. So basically what we do is we take this whole value, since it's not going to be changing, and we'll say that AH times the square root of GH is equal to alpha, right? And what we'll just say is like alpha is equal to some number. So if we set it to like 0.5 or 1, it's just a lot easier that way because it's going to be a constant instead of like writing it out each time. So let's go ahead and head into Python, and first we will calculate our initial steady state values. Okay, so I've gone ahead and imported in some of the necessary libraries and tools that we'll need to be able to solve this problem. Things like numerical Python, JAX, that'll help us linearize around our steady state. And I've also imported like our plotting tools, and then things like the root solver as well, which I will actually, I have the root solver in here, and we'll actually use that to get our initial steady state fluid levels. And then below here, I have that alpha that I was talking about, which is just the cross-sectional area of the hole.
times 2g, and it's raised to the all under the square root, or not all under, just the 2g here. We're going to use this alpha because it'll essentially stay constant for Q1 and Q2. Then we have the cross-sectional area of the tanks. We set that equal to 2. And then we also have an array here of our initial flow rates into the tanks. So U1 we have a 2, U2 is 0.5, and then U3 is 0.4. Okay, so now what I'm going to do is I'm going to go ahead and we can solve our differential equations and then use the root solver to be able to find our initial fluid height levels in the tanks. And that's what we'll use as basically our foundation to be able to linearize around our steady state to solve this problem. So I'm going to define our right-hand side, and we'll have, as always, our independent variable time, and then followed by a vector of dependent variables, which is height. That's what we're trying to solve for. And then we'll also have our inputs here to this problem, which is our flow rates into the tanks, U. So now what I'm going to do is go ahead and unpack both the heights in the tank as well as our inputs, the flow rates. So I'm going to have H1 and H2 are equal to H, and then we'll have U1, U2, and U3 are equal to U. And now what we need is, in order to solve our differential equations, we need to know our flow rates going out of each of the tanks. So we'll have Q1 is equal to alpha. That'll be multiplied by H, the square root of H. So H times, or H to the 0.5 power. And then we'll have Q2, the flow rate leaving the second tank, which is equal to alpha times H. And this is actually H1. And this is actually H2 here. So H2 to 0.5 power. And now what we're going to go ahead and do is return that right-hand side. So solving for dH1 dt or dH2 dt, we'll have to divide over that cross-sectional area. So we'll go ahead and return our array, so jmp.array, because we'll have two heights, right? One H1 and H2. And what we will have is we will have going into the first tank, we have U1, we have U2 going in, and then we have Q1 leaving. So we'll have U1, so U1 plus U2, and then subtract Q1. And then we'll divide that by the cross-sectional area, AC. And then for our second tank, we have Q1 going into it, as well as U3, and then we have Q2 leaving. So we'll have U3 plus Q1 minus Q2 divided by the cross-sectional area AC. And now we can go ahead and perform a root solver on this. Now, we can take note here that we can actually, from here, we can actually just solve this problem by using solve IBV, but that is not the point of this homework. The point is to be able to linearize it and then be able to create a state space model in which we use our transfer functions to then get at our answer, H1 and H2. So what I'm going to do here is use just the root solver to be able to get those initial H values to have a foundation to be able to solve this problem. So we'll go root, and we're going to use the lambda function, and we're going to do that in terms of x, because we already have our right-hand side here. So we'll have right-hand side, and we'll put in our initial values, so we'll just put in 0 for time, x for our h's, because that's what we're solving for, and then we'll have our initial flow rates here, so we'll have u initial. And then what we need to do after this is we need to supply initial guess for the heights in the fluid level tanks, H1 and H2. So I'm just going to guess 1 and 1. Then we need to run this and make sure it works. And it looks like it was able to run here. So what this is telling us is our x value here is what we're solving for. And this is telling us that the height in the first fluid level After a long time, after these initial flow rates have been going and we've reached some steady state, the first tank is 1.562 meters, the fluid level, and then the second tank has a fluid level of 2.103 meters. So what I'm going to do is call these H initial for our initial heights, and then I'm going to grab them in .x so that we have them to go move ahead and actually linearize this problem. So that's what we're asked to do, and the first part of this homework is to find the initial fluid level heights in each of the tanks.
Okay, so now that we have obtained our steady state values for H1 and H2, what we're going to go ahead and do is take a look at our state space model. And essentially what we want to be able to get out of this is we have some time dependent variables, right, H1 and H2, that we want to not be time dependent. We essentially want to linearize them so that we can solve for them numerically. So what we have here in our state space model is this A here is a matrix just of constant numbers here. And then we have it multiplied by the H values that deviate from the initial H values, H1 and H2. So all just linearized here, just fixed numbers. And then we have our, we add on a B matrix here, which is another matrix. We'll talk about these A and B matrices in a second, but essentially it's just a matrix of fixed values. And then we have U here are flow rate deviances from the initial flow rates that we are given in this problem. So if we take a closer look at this A matrix here, what we are looking at here is what is called a Jacobian. So we'll call that JAC for Jacobian. And what this essentially does is it can take multiple functions and basically tell you how dependent that function is upon your dependent variables. So if we take a look just generically here, what we have is we have our partial derivative of, let's say, function 1 with respect to changes in x. And then we'll have the partial derivative of f1 with changes in y, let's say. And then partial change in f2 with respect to changes in x. And then f2 changes in y. So two functions here, and essentially in our case what we're looking at is we have this f1 here, which we can say is our differential equation for the height 1 fluid tank or fluid level in the tank 1. And what this is saying is it is saying what is the dependence of that that height, what is the dependence of that fluid level height in the first tank to H1 and then H2. And then same thing here for our differential equation for the second fluid level height in the second tank. What is the dependence upon H1 and then H2? And then vice versa, what is the dependence of our same function on U1, U2, and then U3? So what we're going to do here is we can actually, instead of doing all of these partial derivatives by hand, we can actually utilize JAX in Python to be able to solve this numerically. So let's go ahead and set up both our Jacobians here, both for our dependent variables height and then our inputs here, our flow rates. So we can go ahead into Python and do that.
Okay, so the way that we'll go ahead and find our Jacobian matrices here with the JAX is by using JAX.Jacobian. So JAX.Jacobian. And we'll want to use our right-hand side function, obviously. And what we want to take in our first Jacobian matrix here, we want to take the partial derivatives with respect to h, the heights. So what we're going to put, when you use JAX.Jacobian, here we start at 0. We have 0 for time, 1 for h, and then 2 for our u's. So we're actually going to put 1 here, and that will evaluate those derivatives with respect to h. So now what we can go ahead and do is we can actually evaluate our Jacobian around some initial parameters, and we have our h initial and u initial here. So what I'm going to do is just name this function because it is a function and set it equal to this. And then we're going to go ahead and evaluate again at our initial condition. So we'll go ahead and put in 0 for time. And we have our h initial that we solved for. That's why we needed to solve for our initial parameters. And then we have u initial, which we already knew. And give this underscore. And then what I'm going to do, for some reason it is still not, that's uppercase. Okay, so and then I'm just going to go ahead and name this JH so that we can go ahead and pull out our matrix here. So if I go and press Shift Enter here, we get our Jacobian matrix. And again, this evaluates all of those partial derivatives of our two functions with respect to h here. And essentially what this is telling us, this negative 0.4 here, this is this right-hand side. This is the dependence of this right-hand side on h1. And then similarly here, the 0 is this same right-hand side's dependence on h2. And then on the bottom here, this positive 0.4 is the dependence of this right-hand side, so dh2 dt on h1, and then this negative 0.3448 is this right-hand side's dependence on u2. So that's what this matrix is essentially telling us here. So now we'll go ahead and get our second Jacobian matrix, our B matrix, when we looked at the state space model. So this top matrix here is our A matrix. Now we can go ahead and get our B matrix, which again is taking these partial derivatives with respect to the u's instead of the heights. So same idea actually. I'm just going to go ahead and copy this over and make what changes that we need to make. So I'm going to call this our JU function. Basically change everything from height to flow rates here. So JU, and what we want to evaluate these partial derivatives at is not 1, the heights, but 2, the U's. Looks like we're good here. We still have our initial conditions, and we need to change this to JU so we can see what we have here. Let's go ahead and run it. And you'll notice we have a 2x3 matrix, and this makes sense, right? This 0.5 is, again, our first right-hand side's dependence on U1. The second 0.5 is dependence on U2. And then lastly, this 0 is this dH1 dt's dependence on U3. And this actually makes sense here because this is dH1 dt, and this has 0 dependence here, this 0 on U3, and that makes sense because U3 is going into our second tank, not our first tank. And then likewise, for our dH2 dt, we have 0, 0. That is because U1 and U2 are going into our first tank and not the second tank. And then we have 0.5 here, that dependence on U3. So now we have both our A and B Jacobian matrices. Okay, so back to the whiteboard. I've gone ahead and written out our state space model just for us to be able to review all together here. So again, this is our state space equation, and essentially what we're doing here is we're looking at two different functions: our change in the first height of the first tank with respect to time, and the change of the height, the fluid level height of the second tank with respect to time. And we've approximated this to be this matrix here, which is just taking the partial derivatives of the functions with respect to h1 and h2, and then multiplying that by our deviation variables here, which is just essentially looking at how much our heights have changed from their initial heights. And then also taking a look at our inputs here, taking the same idea here for our inputs by taking the partial derivatives, and then also looking at our deviation from our initial steady state values. Now what this y is here is something, essentially what we can get out of our state space model. This y here is basically a variable that we can measure from what we have calculated in our state space equation. So what this is saying is that this is some variable that is dependent upon
the state of the system here, x, as well as our inputs here, u. And what we can do is we can just manipulate this equation here to be able to get what value we want out of the equation. So in many different processes, usually what we need is maybe just one or two values to be able to control those values to get the desired system that we want. So what we're going to do just in this situation is we're going to say, okay, we want to find out what is the fluid level in the second tank. That's what's important to us. That's what we're going to want to find out. So what we can do here is we can solve for this variable. We'll call it y, right, for our equation. And we'll have our x's here, which is our height, h1 and h2. Then we have our inputs here, u, right? u1, u2, and u3. And what we're going to do, because we would just want to get h2 out of this expression, is we're going to go make a matrix here of 0 and 1, because what this will do is we'll take 0 multiplied by h1 and 1 multiplied by h2, which will return us h2. And then what we can do here is just make a matrix of 3 zeros and matrix of 3 zeros. So we'll have 0 times u1, 0 times u2, and then 0 times u3. So this whole thing becomes 0, and what we output here is just h2. Now we can do this if we wanted to solve for h1. We can do it if we wanted to have h1 on the top and like u2 on the bottom and have it return a matrix. But like I said, we're going to assume here that h2 is what is important to us, and that's what we want to return. So now what we can do is we can go ahead and code into Python basically our state space model here. And there's something we can actually use in Python. I believe it's called, we use SciPy signal, I think. And then there's a function in there called state space, where essentially I think you just supply like your A matrix, your B matrix, and then your C and D matrix, as well as some other inputs, and that can actually return you the value that you're looking for. So let's go ahead and go into Python and see if we can solve for H2. Okay, so what I'm going to go ahead and do here first back in Python is first to show how we'll actually set up a state space model. So we can utilize, like I said, something called SciPy signal. And I believe I already have this imported. Yeah, I have it imported as sig. So if I go sig.state space, what it's going to ask us to do is supply our A, B, C, and D matrices. So we know that JH is our A, the one we calculated before. JU is B, and then our C is the matrix with 0 and 1, again, because we want to get, in this case, at H2. So I'm going to import an array here. We'll go 0 and 1. And then our D matrix, let me make this lowercase here. Our D matrix, again, is an array with 3 zeros because we don't want to return any of our inputs. We just want to get H2. So we'll go 0, 0, and 0. Oops, one too many zeros. Okay. So this is our, let me get another parentheses in here. So that's how you calculate, not calculate, but this is how you basically set up your state space model like we've already done. But the way that this is actually useful is because we can transform this state space model into a transfer function. So what we can do with that transfer function is to be able to see, well, how does maybe H1, how does it exactly change with some change in U1? Or how does H2 change with some change in H3? And if we get this transfer function, we can be able to then see that. So to be able to transform this into a transfer function, we can actually use SciPy signal as well.
So I believe it's a command. We use SIG, and it is SS2TF. So what it stands for is state space to transfer function. And to be able to transform this, what we need to supply here again is our A, B, and C matrices, as well as what input we would want, or what we would want to have our transfer function with respect to what input. So do we want our transfer function with respect to our first input U1? Do we want the transfer function with respect to the last input U3? So it asks us to basically supply that to see how we want our transfer function to look like. So I'm just going to go ahead and copy over our A, B, and C parameters here. Make sure I get my parentheses right here. And then what I'm going to do is I'm just going to have our transfer function in terms of, or with respect to our third input. So I'm going to put 2 here because the counting starts at 0. So if we wanted our transfer function in terms of U1, we would just put 0. But since I want it in U3, I'm going to put it as 2 because it's our third input. So I believe our parentheses match up here, and let's see and make sure it runs here. And we get an output here basically with 2 different arrays here. So I actually have SciPy signal.ss2f, so state space to transfer function. Basically just the instructions of it pulled up here. And what we can see this returns is basically the numerator and then the denominator of our transfer function. And in the numerator and the denominator, we're going to have some coefficients of our transfer function, which is a polynomial on top and a polynomial on the bottom. And I think I have a picture pulled up of it here. So here is our transfer function, and what this is returning here in the numerator, the first array will be our first coefficient. The second value in that array is the second coefficient, and then lastly is our last standalone value. And then same thing for the denominator. And since we wanted this in terms of U3, we will have U3 off to the side here to incorporate this into the transfer function by multiplying. So again, what we'll have here, this, for example, this U5, this is in the first array, which is the numerator, which will be this value here. So we now have our transfer function here to be able to calculate H2, the fluid height in the second tank, in terms of any change in U3, the flow rate into the second tank. So now what we're asked to do to basically wrap up this homework is to be able to finally use this transfer function that we've obtained from the state space model and basically put in a change of U3 and plot out how H2 will change. So let's go ahead and plot this out and perform that. Okay, so what I'm first going to do is just name our transfer function here. So I'm going to name it numerator and denominator. And then what I can actually do is then create a transfer function in Python here. So if I go sig.transfer function, what it'll want me to do is supply the numerator and the denominator of the transfer function. So if I go numerator and denominator, we'll have that supplied. And then I'm just going to go ahead and name this H2 underscore U3TF to signify that this is a transfer function for U2 when there is some step change in U3. So now what I'm going to do is we can take this transfer function and essentially do a step change. So basically change U3 and see how H2 responds. So if I go H2 U3TF dot step, what this will show us here is our time values here. So this is 0 to about 20. And then this is how the height of the second tank changes over this 20 time period here. So what I'm going to do here is basically unpack this and call the first set of values T because it's time. And the second set of values I'm going to call each H2 deviation. And one thing that I guess I wasn't too specific about is that these values are the deviation from the initial fluid height in the tank. So it's not necessarily starting at 0, meaning no fluid in the tank. It's starting at 0, which is the initial fluid level, and then everything after is added on. So again, just unpacking this into the time and then the deviation from the initial steady state value. So now that we have this unpacked here, what we can do is go ahead and plot this step change up and see how H2 responds. So if I go fig is equal to make subplots, and then I'm going to add a scatter plot. I will have our x is equal to time, right, on the x-axis, and then y is equal to the H2 deviation. And then actually what we're going, remember, because we started at 0, so what we're going to want to add on is our initial steady state height in the tank. So H initial, and because there's two values in H initial, I'm going to want to grab the second one. So 1 initial, because if I grabbed the first one, I'm going to get the initial fluid height of the first tank and not the second tank. So let's go ahead and plot this up and see what it looks like. So this is the step change of H2, how it responds to the increase in U3. Now, basically to wrap up this video, what we're asked to do is we've gone through all this work to create the state space model and then transform that into a transfer function to use it to see how H2 would respond in a change in U3. But we're now asked to use basically solve IVP to solve for H2 and then compare that to what we have obtained doing it this way. So let's go ahead and do that. So I believe we have solve IVP imported up here. Yeah, right here. So we're going to go solve IVP, and we'll use the lambda function because we're looking at the right-hand side here. So we'll have T and then H. So we'll call our right-hand side. We'll have time. We'll have our H, two unknown heights. And then what we'll have for our U values here is U initial. And we'll want to create some step change here. So I'm going to go U initial plus NP dot array, and we're just going to change U3, right? So an array with 2 zeros at the front for our U1 and U2, and then just add 1 on to U initial. So, or not add 1, but have 1 for U initial. So NP array 0, 0, and then 1. Okay. And then what we need is our time stand, how long we want it to run. So we'll go 0 to 20. We'll have our initial inputs, so H initial, right? We'll set the method for computation to Raoul, and then set the dense output. I believe I need to capitalize this. I think I didn't do that last time and it didn't work, but I'm not sure. Set that to true, and go ahead, and I believe this matches up. Let's see, make sure this runs here. So it does run. So what I'm going to do is store this in our result here. So I'm going to call this result, or res for result, run that, and then what I'm going to do here is create some plotting points. So we'll go tplot to be able to plot this and compare it. So tplot will linearly space out some points. So np.linspace We go 0 to 20 and do 100 timestamps. And what we'll want to do here is basically unpack our value here, because what this is going to return is both H1 and H2. H1 will obviously be consistent because we didn't do a step change, and H2 will be changing. So we'll have H1 and H2. We'll evaluate the result at the solution, right, what we obtained, and in terms of t-plot. So now we can basically plot H2 instead of having to plot both H1 and H2. That's all I'm doing there. And let me run this and see if we can just copy this down and just add in a line on this plot here. So we'll go, I'm actually just going to copy this. We'll go x is equal to t-plot, and then y is equal to h2. Delete this out of there. And then get our plot here. So this second, let's see here. So looks like using the transfer function we got to a steady state around 3.55. And using solve IVP, we got to a steady state around 3.79. Now what's interesting is that the solve IVP technically gives us a more correct answer. However, using this method of getting a transfer function is extremely useful because we can evaluate things such as the stability of our system. But that will do it for homework 4 part 1. Thank you for watching.